Okay guys, so welcome to this lecture on solving complex equations. And here we basically going to be looking at what we call imaginary roots as a start, and then we'll proceed into or towards looking at more sophisticated equations involving complex numbers. So, when we first introduced the section, I posed this question: solve for x when x squared plus 1 equals to 0. And if you look at this very carefully, you take the minus 1 on the other side, plus 1 on the other becomes minus 1. So that's what you're really solving for. But this is a quadratic. And you think, okay, it cannot be factorized. Let's use the quadratic formula. So x is equal to, remember, minus b plus or minus the square root of b squared minus 4ac all over 2a. That's a strange, beautiful color there. And so then we go, now a is 1, b is a coefficient of x, which is 0, so it's minus 0 plus or minus 0 squared minus 4, a is 1, c is 1 all over 2a, 2a was 2 times 1. So if I simplify that, that's just going to give me plus or minus, if you have a look, the square root of minus 4 all over 2. Square root of minus 4, we now know that's going to be plus or minus j2 all over 2. And straight away, we have two solutions as expected, plus or minus j. So what we're claiming is if we substitute x equal to j in there, does it make sense? J squared is minus 1. Minus 1 plus 1 is 0. Yes. Minus j squared is minus 1. Minus 1 plus 1 is 0. Indeed, we have found the two roots of that equation. That's quite nice. It's beautiful. It's elegant. So let's proceed into more beautiful equations. So before I do that, I want to look at these called simultaneous equations, or so-called simultaneous equations. If you have a look here, you've got a plus jb is equal to c plus jd, where a, b, c, d are just constants. They're just numbers. So if you look, and if we compare, say, the real parts, if this were to be true, then we know straight away that a must equal to c. And if I compare the imaginary parts, then I must require that b equals to d. Does that make sense? For all, obviously, real numbers, a, b, c, d. So that's pretty straightforward. So when you have this sort of equation, you might think, oh, but hang on, just a single equation. But remember, we have imaginary parts and we have real parts. Let's try to cement this idea with a few more examples. So here it says solve simultaneous equation z1 if z1 is equal to x plus jy and z2 is equal to 1 plus j. Solve for xy when z1 is equal to z2 dot z2 bar. Yo, interesting. Let's have a look at what is forthcoming. Okay, so same problem, and here we go. So firstly, let's look at what is a z2 bar. Z2 bar, learn the lingo, and that is the complex conjugate of z2. So z2 bar, remember, is 1 minus j. So if z2 is 1 plus j, its complex conjugate is 1 minus j. So let's write this equation out. Let's see what we have. z1 is x plus jy. z2, 1 plus j into 1 minus j. I want to take some time and just expand this out by distribution. So 1 times 1 is 1 plus j minus j. And then j times j is minus 1 times minus becomes plus 1. And so this becomes 2. So we know that a number times its complex conjugate is going to be a real number. In this case, it's just going to be 2. All right, everyone's happy with that. So what we are looking at here is solving x plus jy equals to 2. So if we compare the real parts, that's x, that's 2. So it tells me x must equal to 2. the real part, there's jy here, there's no jy there. So it tells me that y must be 0. Does that make sense? Think about it very carefully. Now some of you are still wondering what just happened here. Well, let's cast your mind back a little bit. What is a plus jb into a minus jb? Now be careful. And we know it's a difference of 2 squares, but it's complex. So it turns out this is a squared plus b squared. It's a real number. Please check that. Right, here's another one. If z1 is equal to 1 plus j2 and z2 is equal to 4 cos 60 plus j sine 60, solve z1 minus 2 is equal to x plus j2y. I like this question because you got different forms, representations of the complex number here. So let's look at z2 out of interest firstly. z2, they said, is 4 cos 60 plus j sine of 60. That is pretty straightforward because cos of 60 we know is a half, sine of 60 is root 3 upon 2. Multiply the 4 in there, we're going to get 2 plus j root 3. So in effect, this chappy here basically tells me z1 is 1 plus j2 minus z2, after simplifying, is that guy must equal to x plus j2y. Sweet. Let's gather some terms. 1 minus 2 is minus 1. Okay, j into 2 minus root 3. There's the j, there's the j. And that's equal to x plus j2y. If you look at the real parts, let's separate them out. The real parts tells me that x is minus 1. And the imaginary parts, this is coefficient of j, tells me that 2y must equal to 2 minus root 3. And no prizes for guessing that y is 2 minus root 3 upon 2. Easy peasy. So we're comparing real parts and imaginary parts. How simple is that? Beautiful as well, eh? Yoo, what just happened here? Okay, let's have a look. 7x plus 3y equal to 7e to the what? Oh yes, that's a j pi by 4. Oh my goodness, look at that writing. 7, but we know this is cos of pi by 4 plus j sine of pi by 4. We must be fluent in mathematics. We must be fluent. So we've done so many lectures now on complex numbers. So the fluency must come out, the elegance, the beauty. So this becomes 7 cos of pi by 4 is 1 over root 2 plus sine of pi by 4 is 1 over root 2. Beautiful. Multiply that out. 7 over root 2 plus j 7 over root 2. Now compare the real parts. 7x must equal to 7 over root 2. So the real parts there will tell me 7x is equal to 7 over root 2. So x is equal to 1 over root 2. Beautiful. What is y equal to? Oh my goodness, is this question so simple? So it's 3y, coefficient of j. Coefficient of j is 7 over root 2. And so finally we tell you that y is 7 over 3 root 2. And there's your 1 mark. Simple. Beautiful again. Ooh, what just happened here? Z squared plus z plus 2 equals 0. Solve for z quadratic. So quadratic formula, z is equal to minus b, which is minus 1 plus or minus. Square root of b squared is 1 minus 4. A is 1, c is 2, all over 2 into 1 because it's a 1 there. Let's simplify. Minus 1 plus or minus. That's minus 8. 1 minus 8. Ooh, nasty. Minus 7 all over 2. So how do we write these as roots? Can't take the square root of minus 7? Yes, we can. So we got z1, 2 roots here, minus 1 plus j root 7 all over 2, complex, and, or sorry, z2 minus 1 minus j root 7 all over 2, because the root of minus 7 is of course j root 7. But then we have plus or minus, and hence there we have. Okay, so it's important that you actually understand how these two roots came about, especially with the j sitting in front here. Cool stuff, man. Okay, so what I'm going to do now is try to solve this equation z squared equal to 1. We know the answer is plus or minus 1. So I want to invoke this complex attribute to this number z. So if we go back and you recall from your Argand diagrams in the previous lecture, this is the imaginary axis, this is the real axis. So where is this number 1? I want to basically focus on 1. So I'm going to call that p equals to 1 and treat that as a complex number. So if I plot it, there's 1 over here. All right. So you'd say straight away, you can see that theta is 0. But is that the only angle that will produce p equal to 1? And you'll say no, because if we add multiples of 360, we'll keep coming back to that point. And we also know the length of that purple vector is what? Yes, it's 1. And you remember that we can write this as mod z e to the j theta. So the length of the line mod z we know is 1. E to the j theta, watch this, in most general form is j. We know it's 0 plus 2k pi. So we tag this on to the principal value, and we get 2k pi. So the number 1 is nothing more than e to the j 2k pi. So if 1 is that, then we can write z squared is equal to e to the j 2k pi. And if I take square roots, then I know z is equal to the e to the j k pi. You agreed? Because you're taking square roots on both sides, the 2 is going to go away. What does this mean? So z squared, we need 2 solutions. So here are our 2 solutions from here. Solution 1 is when k is 0. When k is 0, we'll get z1 is e to the, obviously, 0, which we expected was 1. The second solution when this k is 1. So we get z2 is equal to e to the j pi. But what is e to the j pi? It's minus 1. How did I get that? You can see I miss art class, yeah? So e to the j pi, why is that minus 1? So let's go. Z2 is e to the j pi in polar form, that is cos pi plus j sine pi, and that is cos of pi is minus 1, sine of pi is 0, and everyone's happy. How sweet is that? So we reproduce the 2 roots that we guessed, plus or minus 1 for z, using the complex approach, using an Argand diagram and the principal value, but the more general value for that. Awesome. That's pretty cool. Whoa, z squared equal to minus 1. You know what I'm going to do here? I'm going to take this minus 1, I'm going to call that p. And I want to represent p on the complex plane. So there's my imaginary section. There's my real section. And then where's minus 1? Well, minus 1 is here. That's minus 1. But so what is the angle? So it tells you straight away the principal, or the arg z, remember, is pi. Or arg p in this case, not z, arg p. Capital A. Let's get this right. Let's get this right. Arg p is pi. But we know that if we keep adding stuff, if we keep adding, and we're going to keep coming back by adding 360 to it. Oh, that's nasty. It looks like a spiral, Archimedean spiral. I didn't mean that. If we keep adding to the principal value of p, I'll come back to that red vector. And we know that the magnitude of this vector, P, the magnitude, so if I can write this as, I don't know why I said that, it's actually magnitude P e to the j theta is 1. Okay? Because remember, magnitude P is the real part squared plus the imaginary part. There's no imaginary part there. That's plus 0, j0. So that's 1, not minus 1. E to the j theta is pi plus 2k pi. I hope you're with me. Pi plus 2k pi. If we just wrote pi, we're just going to get one single principal value. And we know that, the periodicity of the cos and sine functions is 2k pi. So what are we solving for? We're solving for, in effect, oh, that's a nasty color. It's like a mangoish color. Such a word as mangoish. It's a beautiful color. And P we said was this guy, so it's e to the j pi plus 2k pi. If I take the square root on both sides, then I'm going to get e to the j, watch this, pi by 2 plus k pi. And if I want the two roots, watch this, the first root is when k is 0. So when k is 0, you can see straight away that z1 is e to the j pi by 2. Now e to the j pi by 2, if you transform that into polar, that's cos pi by 2 plus j sine pi by 2. So that's going to be j. There are no prizes for guessing. We know that j squared is minus 1. What about the second root? Let's go on to the other side here. This is so beautifully colored here. Different colors, spectacular. This is when k is equal to 1. When k is 1, then the second root is z2. When k is 1 there, we're going to get e to the j 3 pi by 2. Right? And that should be minus j. So minus j squared will give you minus 1. And there we have it. Everyone's happy. That's the general solution. Straightforward. Oh my goodness, z cubed equal to j. No prizes for guessing over here. You can see the theme and how it's developing. It's pretty straightforward. This is the imaginary. That's the, where is j? Where is j? J is up there. It's imaginary right up there. What's the length of the green line? The length of the green line is 1. So if I want to write this number, pj, p equals to j, how do I write it in complex form? Well, that's going to be the mod p e to the j some theta. Well, the theta, the argument, capital A, arg p is pi by 2. You can clearly see that. It's 90 degrees. But the more general one is pi by 2 plus 2k pi. And what is the size of this guy? The length p, don't forget, is the root of 0 squared plus the coefficient j is 1 squared. So it's 1, not j. So this is 1 e to the j pi by 2 plus 2k pi. That's p. But we don't want p. We want to solve for z. So it's e to the j pi by 2 plus 2k pi. Take the cube root. E to the j pi by 6 plus 2k pi all over 3. So how many roots do we have? Or how many roots do we need here? Well, we need 3 roots. Too much of purple, eh? First root z1 is when k is 0. So when k is 0, this term is gone. So we get e to the j pi by 6. So let's test that. Cos of pi by 6 is root 3 upon 2. And then we have cos of pi by 6, which is 30, which is sine. And if we cube that, I want you to check that out. If we cube that, do we actually get j? So let's just test that, and then you can write down the other 2 roots. So this would be cos of pi by 6, right, plus, watch this, j sine of pi by 6. Now, if you cube that, do you get j? Let's see. And we use de Moivre's theorem, yeah? So if z1 cubed, that's pretty straightforward. That becomes cos of 3 pi by 6. 3 pi by 6. Watch and learn. Beautiful. Plus j sine of 3 pi by 6. Cos of pi by 2 is 0. That's, and the answer is j. Yippee! It works. J z cubed is equal to j. So one solution here is cos of j pi by 6, which if you had to write down, cos of pi by 6 is root 3 upon 2. Sine of pi by 6 is a half. So z1 is root 3 upon 2 plus j half times half. And don't forget, if you write down z1, then you need to also write down z2 and z3, where you let k equal to 1 and k equal to 2 respectively. You've got to write down all 3 roots. Thank you very much. Aibo, z squared equals to 1 plus j. What is this? Well, p is equal to 1 plus j. And into the complex plane, keep reminding you, imaginary, real, where is 1 plus j? We know there's 1, so it's there. And we know from the previous videos, the length of that vector, and if you know this is p e to the j theta, well, the principal argument, arg p, in the first quadrant, that angle theta is pi by 4. But we know that's not the only angle, because this can come through another, yeah, we keep adding 2 pi. But we know that mod p is a root of 1 squared plus 1 squared, which is root 2. So this is root 2 e to the j, watch, pi by 4 plus 2k pi. So what we're solving for finally is z squared equals to root 2 e to the j pi by 4 plus 2k pi. And if I want to write down me 2 roots, like that, the first root is when k is equal to 0. That is z1. And if k is 0 over here, then we're going to have, I'd forgotten to take the square root. So we take the square root, that is 2 to the power half. The square root of 2 to the power half is 2 to the power quarter. And then we got e to the j, watch this, pi by 8 plus k pi. Right, neatly. So z1 when k is 0, that's gone. So that's 2 to the power quarter e to the j pi by 8, and which you can write out in polar form. And then the second root is when k is equal to 1. When k is equal to 1, you have z2 is equal to 2 to the power a quarter e to the j, watch this, so that's going to be pi by 8 when k is 1 plus pi. And that's it. That's really it. Those are your solutions, and you're done. Beautifully done. Brilliant. Okay, what have we here? Well, z to the power 4 equal to minus j 4 roots. Well, very quickly, we're going to go p equals to minus j. So if you have a look here, where is minus j in our complex plane? So this is imaginary, this is real. Minus j is, of course, down here. Okay. And now this is beautiful because we write this as mod e to the j theta. Well, we know the size of that is 1. Red line, the length of that vector is 1. The angle, my friends, the angle cannot be this okie here, but it's this okie over there. So the angle theta, so we say arg p is minus pi by 2, but that's not the most. We can keep adding on. We can keep adding on 2k pi. So so this number minus j can be written as 1 e to the j. Theta is minus pi by 2 plus 2k pi. So if I want to solve z to the power 4 equal to e to the j minus pi by 2 plus 2k pi, we take the fourth root on both sides, and there we have it. E to the j minus pi by 8 plus k pi by 2. Hey. Done. Sorted out. So how do we get the four roots? Four roots are very simple. The four roots corresponds to k equal to 0, k equals to 1, k equal to 2, and k equal to 3. Let me show you. K equal to 0, that's 0 there. So then the first root is z1. Too much of purple, yeah? Is equal to e to the j, well, minus pi by 8. There's a minus sign, I'll throw it in front. Here, nasty. Right, and the next one is, of course, z2 when k is 1. What is that? So that's 2 is 8. 4 times 4 pi minus pi is 3 pi by 8. So this becomes e to the k, not kj. So untidy as well. So e to the j 3 pi by 8. That's actually a positive number. Let's get rid of that. That looks like a nasty minus sign there. This was minus. Please write neatly. I'm just such a bad example of what writing should be like. And then you can go on for k equal to 2, k equal to 3. Please complete, please complete. And you can write this out in full. Because remember, cos of minus j pi by 8 is cos of minus pi by 8 plus j sine of minus pi by 8. So you can write that in rectangular form. And in fact, examiners want you to write each of the roots in rectangular form. So get into the habit of actually doing that. That's pretty awesome, guys. So hopefully you enjoyed that lesson. It was a really cool tour of finding roots, solving complex equations, bringing it all together. Dumoir's theorem, Argand diagrams, the quadratic formula, simultaneous equations, comparing coefficients. This lecture had everything in it. It's like a James Bond movie. Awesome, guys. So can't wait to see you on the other side of 11, whatever that means. Cool stuff. Stay safe.